Hello Calc students, here we are with limits at infinity. These are things we've done already when we looked at things like what happens with the graph of something like this, y equals 1 over x. As x goes to infinity, y approaches 0. We've talked about that as a horizontal asymptote. Now we're going to look at that a little more formally now with our definition of limits here. Limits at infinity. We can look at the end behavior of this graph, 3x squared over x squared plus 1. And we can see that as you head off to infinity, you get closer and closer and closer to 3. As you head off to negative infinity, it also heads closer and closer to 3. So we call that a limit at infinity. It's never going to quite reach 3 because you always have this plus 1 on the bottom. So it's not quite 3x squared over x squared. It's always going to be a little less than 3. So here's a formal definition. I'm not going to require that you know this formal definition. It's just this idea of an epsilon delta proof again. That is, there's no delta. That is, if someone picks an epsilon, there's a certain closeness you have to get to this limit. If you go far enough out with x, you'll get that close. So it's the idea of getting closer and closer, and that is arbitrarily closer to. So now let's explore this with a graphing utility. This function, 2x squared plus 4x minus 6 over 3x squared plus 2x minus 16. And we see some strange behaviors here. Something like this we've seen before. These are the vertical asymptotes. And remember where that comes from? What makes the denominator equal to 0. But we also see in this thing a horizontal asymptote. As x heads off to infinity, in both directions we see getting closer and closer to a level somewhere here between 0 and 1. And what does that turn out to be? Looks like about somewhere between about 2/3. And as we're going to see, we can predict it from these coefficients on the leading term. Now, here's a few general rules. The line y equals L is a horizontal asymptote of the graph if, as x goes to negative infinity, you approach L, and as x goes to positive infinity, you approach L. That's our definition of horizontal asymptote. And that's what's going on over here. We've got a horizontal asymptote at y equals 2/3. As you recall, these were the vertical asymptotes. Those are the things that make the denominator equal to 0. Now, limits at infinity. If r is a positive rational number and c is any real number, then the limit as x goes to infinity of c over x to the r equals 0. Furthermore, x to the r is defined when x is less than 0. If it's defined when x is less than 0, then the limit as x goes to negative infinity of c over x to the r equals 0. The most common application of this is the limit as x goes to infinity of 1 over x. In this case, r equals 1, the constant c is 1, and that was equal to 0. We talked about this before as the bottom growing faster than the top, and that's going to happen if you have a constant on top and you have some positive rational number on r. Now it could be any positive rational number. It could be even x to the 0.01 power. This will approach 0 because eventually this will grow and 1 will not. Finding the limit at infinity then, here's the algebraic approach to something like this. We can say the limit of a subtraction is the subtraction of limits. So the limit as x goes to infinity of 4 minus the limit as x goes to infinity of 3 over x squared. Well, this is just going to approach 4 because x is changing but 4 is constant. Here, as x goes to infinity, this bottom gets huge. So even though we start with a 3, and when x equals 1, you get 3, but when x equals 1,000,000, you got 3 millionths squared. So this is essentially 0 then. And there's your algebraic approach to that limit. Now here's the graphical solution. You put in your graphing calculator and see what's going on as you start heading further and further down the graph. So y equals 4 is a horizontal asymptote to the right, and also to the left. Finding a limit at infinity. Now to find this limit, this gets a little trickier here because now we got unknowns in the top and the bottom. So here's our Fomer approach, because essentially we're going to get infinity over infinity if we just try and plug in infinity. I think a lot of kids see that if you put infinity in the bottom on this, you get 0, and you're left with 4. But here what we can do, to use the rules we had before, is I'm going to multiply the top and bottom by 1 over x. So it becomes the limit as x goes to infinity of 2 minus 1 over x all over 1 plus 1 over x. So it becomes the limit as x goes to infinity of 2 minus the limit as x goes to infinity of 1 over x all over the limit as x goes to infinity of 1 plus the limit as x goes to infinity of 1 over x. See, I can sort of distribute the limit idea over division and subtraction. And so these then end up being, the limit as x goes to infinity of 2 is just 2, because 2 is a constant, it's not affected by x changing. But this we just talked about, that's getting closer to 0. And this gets closer to 1. And this is 1, it doesn't change, and this gets closer to 0. So you get 2 over 1, which is 2. Now, we've talked about this when we looked at horizontal asymptotes, that we can, if we've got the same degree in the top and bottom of a rational function, we can just look at the ratio of the leading coefficients. I also wanted you to see this technique too, though, so you can see more of a formal proof of why that limit works. Now let's look at these three rational functions. And again, to deal with each of these, we can multiply by 1 over x cubed, in this case 1 over x squared, by 1 over x squared. So this gives the limit as x goes to infinity of 2 over x plus 5 over x squared all over 3 plus 1 over x squared. And so these terms are all going to go to 0. And so we get 0 plus 0 over 3 plus 0. Essentially just get 0 over 3, which is 0. So that's a little formal proof of what we knew from before, that if the bottom degree is higher than the top degree, then the bottom is going to grow faster than the top, and the whole thing will just approach a horizontal asymptote of 0. Here, I'm going to multiply by 1 over x squared all over 1 over x squared again, just to make this the limit as x goes to infinity of 2 plus 5 over x squared all over 3 plus 1 over x squared. And again, these go to 0 and you just get 2/3. That's that ratio of the leading coefficients we talked about before. If the degrees are the same, they're going to grow just as fast as each other. Essentially, this turns into 2x squared over 3x squared as x goes to infinity, or 2/3. Finally, let me pop C up on another page here. For part C, limit as x goes to infinity of 2x cubed plus 5 over 3x squared plus 1. I'm going to multiply top and bottom by 1 over x cubed, but that's not going to quite do it. Let's just multiply by 1 over x squared. You can see where we've got some problems here. It's not going to boil down for us. As x goes to infinity of 2x plus 5 over x squared all over 3 plus 1 over x squared. So it's a limit as x goes to infinity of 2x over 3, which is basically unbounded. See, these disappear and go to 0, but then we still have this x up here. The top is growing faster than the bottom, so you don't get a horizontal asymptote. Instead, this approaches positive infinity. Now, as we go off to negative infinity in this one, we'd head toward negative infinity. So here's some guidelines for finding limits at infinity of rational functions. And this is what we just talked about. If the degree of the numerator is less than the degree of the denominator, then you've got a limit of 0, horizontal asymptote of 0. If the degrees are the same, then you look at the ratio of the leading coefficients. And if the degree of the numerator is greater, then the limit of the rational functions does not exist. You can mention what infinity goes to as some sort of end behavior. Here's a little side note, and I enjoy reading these from out of the book. Maria Agnesi, famous mathematician. Take time to read that. And here's one of her graphs, which has a horizontal asymptote of y equals 0 because the degree on the bottom is higher than the degree on the top. And Mary came up with a whole class of these functions that have this type of symmetry and almost look like the bell-shaped curve you see in statistics. So let me know if you think that this is the same as the bell-shaped curve or different. Now, our last set of examples here is what happens when you have a function with two horizontal asymptotes. These are very tricky to do algebraically. I suggest you analyze them with a calculator. Let me show you what's involved with some of the algebraic approaches on this one. The limit as x goes to infinity of 3x minus 2 over square root of 2x squared plus 1. This is very hard to deal with just in terms of what degree is this on top. This is 1 on the top. On the bottom, it's the square root of something squared. So, you've got many approaches on this. Let's start with this idea. Okay, we're going to take on this one on the next page. Oops. Take this one on the next page, but so let's focus on this one right now. The limit as x goes to infinity of 3x minus 2 over 2x plus square root of 2x squared plus 1. Well, I'm going to multiply top and bottom by 1 over x. And at first that seems like it's going to make the top okay. But what happens on the bottom? So you have the limit as x goes to infinity of 3 minus 2 over x all over square root of 2x squared plus 1. And I'm going to rewrite x as the square root of x squared, so I can sneak it inside that square root. Now, since x is approaching positive infinity, we're going to assume we're way out there. So x is greater than 0. That means the square root of x squared, which normally equals the absolute value of x, since x is greater than 0, that will just equal to x. We're going to see the opposite is true when we take on this one as we approach negative infinity. So let's keep working with this then. Limit as x goes to infinity of 3 minus 2 over x all over square root of, now let's sneak this inside and we get 2 plus 1 over x squared. Now we can try and evaluate this limit. The limit as x goes to infinity of 3 is just 3 minus 2 over x. As x goes to infinity, that's just going to be 0 all over the square root of 2 plus 0. So we get 3 over the square root of 2, or 3 root 2 over 2. Either of those is fine. So that's the limit in that direction. Kind of like these leading coefficients here. If you kind of ignored the plus 1, you'd have the square root of 2 times x there. Now, in this other scenario, though, this is as, since x is approaching negative infinity, that means x is less than 0. So the square root of x squared, which equals the absolute value of x, is equal to the opposite of x. So x will equal the opposite of the square root of x squared. So that's going to have a bearing on how this works out. When I multiply top and bottom by 1 over x, we're going to get the limit as x goes to negative infinity of 3 minus 2 over x all over square root of 2x squared plus 1 all over negative square root of x squared. Because x isn't equal to the square root of x squared, in this case, as we're approaching negative infinity, it equals the opposite of the square root of x squared. So it's the limit as x goes to negative infinity of 3 minus 2 over x all over square root of 2 plus 1 over x squared. Let's not forget that negative sign. So we get 3 minus 0 over negative square root of 2 plus 0, or negative 3 over the square root of 2. And so this is one of those bizarre situations where we can have two different horizontal asymptotes depending on which direction we're approaching. If we approach positive, x approaches positive infinity, the y's are getting closer to the 3 over square root of 2. Negative infinity, as x approaches negative infinity, then our horizontal asymptote is y equals negative 3 over the square root of 2. Okay. So rational functions, we have a ratio of two polynomials. Those will always have just one horizontal asymptote. But it's possible for these non-rational functions to have different horizontal asymptotes depending if you go to the right or to the left. Now, there's our formal definition of limits, of infinite limits at infinity. So rather than saying the limit does not exist, is say the trend it's going in, like say either, it's unlimited, but it's going toward positive infinity, or if it's going toward negative infinity. And so in this case, when we look at y equals x cubed, the limit as x goes to positive infinity is positive infinity, and as x goes to negative infinity, it's negative infinity, as we see in this graph. Now finding infinite limits at infinity again, here's another example. Limit as x goes to infinity in this situation. What we mainly want to see here is what is the behavior of this function as we head off to the infinities. And one way to do this is to actually divide this out and put it in negative 1 and divide out this polynomial 2, negative 4, 0. and we get 2 times -2, -6, 6, 6. So we could also look at this as the limit as x goes to infinity of 2x minus 6 plus 6 over x plus 1. So basically this thing is going to act like 2x minus 6 is going to act like this line. In fact, this is the slant asymptote we looked at before. And y equals 2x minus 6. I'm sorry, I have the wrong negative sign in there. Oh yeah, 2x minus 6 is our slant asymptote. Right. And as x heads toward positive infinity, the limit as x heads towards positive infinity of this function, 2x squared minus 4x over x plus 1, will equal positive infinity. Because it's going to act like the line y equals 2x minus 6, and as you go from left to right, you head toward positive infinity in that direction. As you go from right to left and have x's approach negative infinity, then the y's approach negative infinity. So the limit as x approaches negative infinity of 2x squared minus 4x all over x plus 1, that equals negative infinity. Now, don't get the impression that just that this infinity after the x, it matches the infinity on the y. It's only in the case of this one because we have basically a positively sloped line for a slant asymptote. If the slant asymptote ended up being negatively sloped, we'd get a different answer. Okay? Flange out.